Can you hear me?
Yes.
Yeah, okay, very good. Thanks. So I might be picky, but it looks like WZ is below the theory prediction. Is it correct?
Yeah, that is correct, and
Yeah.
that's
So,
good.
yeah.
Yeah, go ahead. Sorry.
So okay, are people looking into this, or this is the final result, and you just leave it as it stands? Or are there attempts to understand it, or are you not worried? I mean, when you
Yeah, we have investigated this like problem, but that is because the data Monte Carlo agreement, and when we perform the likelihood fit, the signal strength in the case of the WZ is like 0.6, and that's because it is away from the prediction. And in the case of the other channels, the signal strength is close to 1.
Okay, so this is, you will leave, I mean, it will stand like this, I guess, until we have a next 5 TeV PP collider. Whenever that will be. Okay, thanks.
Actually, along those lines, is there on the theory side an estimation of the error associated with the jet veto scale? I think you chose 25 GeV. That jet vetoes usually introduce large logarithms, and so I wonder if they've tested how the theory prediction changes if you relax the jet veto versus making it tighter.
Yes, actually, we investigate this when we were doing the review of the analysis, and this has not changed the result a lot.
I see. Okay, so it hasn't played much role. I have one more quick question, which is regarding the pileup. You had said that these were sort of very low pileup compared to, say, 13 TeV. And I think at 13 TeV, there's like, I think pileup is something like 40 events. Is that right? And whereas at 5 TeV, you said it's much lower. Like how much of a difference is there in pileup uncertainty with 5 TeV versus 13 TeV, for example?
Okay, I'm not sure. I will have to check this, but yes, we compared, and we saw that the pileup was lower than at 13 TeVs, but I'm not sure of the numbers right now. So sorry.
Yeah, no problem. Any other questions for Andrea? All right, if not, thank you, Andrea, and we'll move to the next talk, which is from Matous Vozak, who is going to tell us about measurements of multi-boson production at ATLAS. Take it away.
Hi, can you hear me?
Yes.
Perfect. Okay. Well, thank you a lot for the introduction and for the invitation. And I'm happy that on behalf of ATLAS Collaboration, I can present to you this talk about measurements of multi-boson production at our ATLAS experiment. So go immediately on the next slide. ATLAS has an extensive program where it measures events with 2 and more bosons being produced in the proton-proton collisions. And these do not provide only precise tests of standard models, but also necessary inputs to search for the physics beyond. And I'm going to talk in this talk about 3 recent measurements by ATLAS, all of which end up in a slightly different final state. And I'm going to start with the inclusive 4-lepton measurements, an example of which you can see on the right-hand side. So this analysis is looking inclusively in production of 4 leptons, where it requires 2 pairs, and each pair is the same flavor opposite sign lepton. And this gives you a few of the combination depicted in here, where either electrons and muons are produced. And to increase the inclusivity, we also add the decays from tau leptons. Now this can lead to quite a lot of standard model physics. And what you can see in here is the invariant mass of the 4-lepton system with variant contributions. And the dominant is the quark-initiated ZZ production in the red in here, but you also have additional contributions such as the gluon-gluon ZZ production in orange, or for instance, Higgs, tri-boson in yellow here, TT bar, and potentially any other physics which ends up in this same final state. One additional thing that you might notice in here is this pink background. And the most dominant background in this analysis comes from the fake leptons, which arise from the decays of heavy or light flavor quarks. And because this is not very well modeled background, we use data-driven methods, and in particular the fake factor method, which simplified example of one lepton case you have in here, where at the core of the method you have this efficiency of your fake leptons to be reconstructed as a signal leptons, and then you can use this to derive the equation between the number of the fake leptons that pass your signal selection and number of the leptons that fail your signal selection. Now, obviously, in the 4-lepton case, this is a little bit complicated because you have these additional contributions from different cases, from free to fake leptons and so on. So all of these have to be then included in the final estimate. At the same time, this method has been validated. If you remember, I mentioned that we use the same flavor opposite charge leptons in the pair, but for the validation, we use the different flavor opposite charge and same flavor, same charge. Overall, the contribution of this background is 4%, but as you've seen in the previous slide, it falls very quickly with M4L value. The only remaining background that we have is Z plus epsilon, which is derived from the Monte Carlo and is very negligible. We use two-fold correction in this analysis. The first one is standard iterative Bayesian unfolding that corrects for the resolution effects. But in addition, we also apply the pre-unfolding correction, which is applied in order to minimize the dependence of the underlying standard model lepton kinematics. And this is applied per event by using this weight in here, where you have 1 over product of efficiencies of your signal leptons, and these are derived separately for the cases where lepton decays from tau and naught, because they are quite different. Now, if you may wonder what is actually the effect of this, so we've performed various injection tests with the beyond standard model of physics signal, where we injected the signal, then we applied this full correction procedure, and we compare the unfolded results with the true. And the result you can see in here, where you have 2 lines. The green one, it shows you if we do not apply this pre-unfolding correction, and the one in black is width, which closes much better. Now for the results, the analysis provides various single and double differential cross-sections, where example on the left-hand side, you have here inclusive M4L, where the data is in the black points, and then you have comparison of 2 generators, Bauheck in the blue and Sherpa in the red, which are quite consistent with each other. But you may also notice that there are these lines which suggest separation in the M4L into 4 main regions, which is off-shell, on-shell, Higgs, and Z. And in these specific regions, we measure also additional variables, for instance, the polarization variables, an example you have on the right-hand side in the Z region. In addition, analysis also provides integrated fiducial cross-sections in the full phase space, but also in these regions that I've just mentioned. And in addition, in particular, the Z into 4L is then used to extract the branching fraction of this process, which provides most precise results up to date that are compatible with the Monte Carlo Bauheck prediction. These inputs are also used to set the limits on 2 specific beyond standard model scenarios. The first one is the local gauge B minus L symmetry that is spontaneously broken, and as such produces an extra particles, for instance, the exotic Higgs that mixes with the standard model via this angle alpha. And you can see the scan phase space plots below, where we have this alpha parameter and the mass of exotic Higgs. And what you can see on the left-hand side is basically the most sensitive variable at the given phase space, so kind of suggesting that you can benefit from having multiple measurements of different phase spaces. And on the right-hand side is the normal exclusion plot with observed exclusion in the red and expected in the black. In addition, we also test our results with the effective field theory, where the standard model is extended by these extra dimension operators parameterized by the coefficients seen here. And the analysis is in particular sensitive on dimension 6 coefficients, sets limits on 22 of them. Example you can see here below, where you have the name of the coefficients, the most sensitive variable coming from the infrared measurement, and then in the red you have the observed limit at 95% confidence and expected in the shaded. In addition to the full model, which includes not only the interference with the standard model, but also the purely EFT term, results also provide only the linear terms and then compares them together to sort of suggest if there is any missing contribution for a higher dimension coefficient. The second analysis is looking at the events where we have the gamma and Z boson that decays into BB bar. And these are then subsequently reconstructed using the anti-KT algorithm in the large jet, and then groomed for mitigation of the pileup and underlying event. In particular, two different techniques are being used. The one is sort of Atlas standard for the boosted topologies, trimming technique, and the other one is soft drop, a relatively new technique that achieves higher theoretical precision. It's important to study this because we have various rare processes, either from standard model or from beyond, and which can end up in the same final state. And therefore, measuring this in the Z can improve our understanding and the precision. And lastly, as I was saying, there is a gamma in the process as well, which is what this analysis triggers on and allows to measure in the low PT of the Z. The dominant background comes when we don't have the Z, but gluon decaying into BB bar. As you can see, it's quite dominant background. And therefore, a data-driven technique is used to estimate this background, where we basically separate phase space into identification of the gamma and also in the number of the B jets. And the assumption is that if we construct the transfer factor, which is basically number of events passing the selection divided by not passing the gamma selection, these would be identical regardless of how many B jets which we have. And that's exactly what you can see on this plot below, where you have the comparison in 0 and 1 B tag jets. And applying this, we can transfer this into our signal region and derive the estimates. There are additional contributions, big contributions, but they are quite small, and these are predominantly taken from the Monte Carlo predictions. Now, once we have the background estimates and the signal, we use both of them and perform a fit using the binned maximum likelihood. And on the bottom, you can see the jet mass in both techniques trimmed on the left and self-drop on the right-hand side, where the data is in the black points, the signal is in the red, and the dominant gamma plus jet Monte Carlo in the blue. And below in the ratio pad, you can see the comparison data with the fit. On the right-hand side, you can see the measured yields in all of these processes in both of the techniques, and below is the computed significance for the both. And you can see that there is a bit difference between the techniques, but that mainly comes from the difference in the cross-section and also the performance in the mass resolution. In addition, analysis also provides the integral fiducial cross-section, where we have the measured cross-section for both techniques with the statistical uncertainty, which is the dominant, but also the systematic uncertainty, and then comparison with two Monte Carlo predictions, one from Sherpa and the other with MatGraph. And on top of that, analysis also provides differential cross-sections in the jet mass, where on the left-hand side, you can see the trimmed result, and on the right-hand side, you can see the self-drop results, which seem to be more symmetric around the Z mass value. Lastly, I'm going to talk about the measurement of WW with inclusive production of jets. This is actually the first kind of a measurement by Atlas, inclusively in the number of the jets. And as the jets are produced in the ISR, it provides a good test of predictive QCD physics, but also this process usually represents quite large background in various Higgs measurements and beyond standard model searches. Therefore, it's quite important to understand this process well. In addition, analysis also tries to perform the setting limits on the anomalous triple gauge coupling. The dominant background in this process comes from the top quarks, and the main contribution is from the TT bar, even though the analysis performs B beta. And therefore, again, data-driven approach is being used to estimate this background. The analysis defines specific 1 and 2 beta control regions, which are TT bar dominated. And then basically using the relation of these beta regions with the signal region through the beta-tagging efficiency, you can derive this master formula, which, as if you notice, it depends mainly on the measured yields of these specific control regions purely, which are derived from the data. As I was saying, there's additional contributions of WT, but that's derived from the Monte Carlo. And then eventually validation region is being constructed, which is enhanced in the top contribution, and the method is being double checked that everything fits well. There are additional backgrounds in this process, but they usually represent only a couple of %. But every one of them is separately validated in the respective regions. As a result, for this analysis, it provides the fiducial cross-section, where after the measured yields are being subtracted by the background, they're subsequently corrected for detector effects. And you can see the results in here, where the dominant uncertainty is the systematic uncertainty, mainly coming from the jet energy scale and jet calibration, and following by the top modeling. The measured results are also compared with the state-of-the-art Monte Carlo at various precision level, and each one of them seems to be consistent with the results. The analysis also provides quite a lot of measured differential distributions. I've just picked 2 of them to show you. What's on the left bottom is the differential cross-section of the invariant dielectron system, and on the right-hand side is the polarization variable. And you can see that the measured data seem to be quite consistent with all the predictions. Lastly, as I was mentioning, analysis also tries to set the limit on the anomalous triple gauge coupling using the invariant mass. And in particularly, it was trying to look at how the sensitivity to this parameter of interest can be increased with the high PT of the jet. And what you can see in here is that in addition to the nominal phase space, it also defines additional phase space with the presence of the high PT jet. And in particular, linear limits on this is quite reduced, as you can see in the blue lines in here. So to summarize, I'll try to introduce you to 3 recent Atlas multi-boson measurements. And all of these are providing the measurements of the integral, but also differential cross-sections. I've talked about various techniques that have been adapted to reduce the model dependency. Some of the measurements are using various techniques to probe the jet substructures to study the boosted topologies. And also the several scans were performed to search and navigate for the physics beyond the standard model, such as the EFT B-L, anomalous triple gauge coupling, and so on. And I'll leave you with just an example of such a scan in here below from M4L measurement. Thank you.
All right, thank you. Any questions from anyone? I had one question on your Z plus gamma, the Z to BB bar plus gamma, where you applied soft drop. Did you guys, I was just curious what the groomed jet mass, sorry, what the groomed jet radius looks like. Is it very close to R equaling 1 because the 2 B quarks have to kind of, they stop soft drop? Like, so if you start with a jet radius of 1, what is a typical jet radius after grooming?
You mean when you do recursively and go back then?
Yeah, so after you apply soft drop to the jet and you trim, you groom away some particles, then you're left with some new groomed jet radius,
yes,
which will be less than 1. So I'm just wondering if you guys looked at distributions in that as to what typical values are.
I think I have one slide for this. Let me see if I put the values in there. Okay, I don't think I have the values in here. I think they're quite different between the two. And to be fair, I'm not 100% whether several different R values have been tested. But I think, if I'm not mistaken, 0.2 value was being used. But it's probably better to double check with the paper.
Okay, I was just kind of curious because this is sort of a Z decaying to 2 B quarks, and so the soft drop presumably mostly stops on the 2 B quarks, which are always in the Groom jet radius. So it kind of may tell you something about the angle between the B quarks. Anyway.
I see.
Any other questions from anyone? All right, thank you. Now we'll move to the next talk, which is by Pedro Fernández Manteca, who's going to tell us about W pair production at CMS. Take it away.
Hello, do you hear me?
Yes.
And you can see the screen, right?
Yes, we can see your screen. Yeah.
Okay. So thank you very much for the invitation. And well, I will be talking about WW boson pair production at 13 TeV using CMS data. So basically, I will show you the results for this from this recent physical review D paper that uses the full 2016 CMS dataset. And the analysis itself is based on 2 different approaches. So we have the sequential approach, in which sequential selections on kinematic variables are used. And then we have the random forest analysis, where a multivariate technique is built just to get a purer WW selection. So the goals of this paper are to measure the total WW cross-section in the dielectronic channel, to measure the fiducial and differential cross-sections as function of several kinematic quantities, and to set constraints on the Wilson coefficients from anomalous couplings. And on the bottom of the page, we can compare the last published result from CMS for the total WW cross-section with the one delivered by this new publication. And indeed, you can see that we have improved quite a lot the precision on this measurement. So let's begin with the sequential analysis. So we target the dielectronic final state. So the signature basically consists of 2 opposite charge isolated leptons and large transverse missing energy from the neutrinos. And this sequential analysis relies on a set of discrete requirements on several kinematic variables, and then on a multivariate tool to suppress the Drell-Yan contribution in the same flavor channel. So the applied event selection is the one described on the table. So for the different flavor channel, we require 2 opposite sign leptons with transfer momentum greater than 25 and 20 GeV. We set a minimum on the dilepton mass and on the dilepton momentum to basically avoid low mass resonances and fakes. Then we select on the missing transverse momentum and on the projected missing transverse energy over the lepton direction, just to reject the Drell-Yan and to account for the neutrinos in the final state. And finally, we select events with 0 or 1 non-B-tagged jets to suppress TT bar. So this is for the different flavor channel. And then for the same flavor category, we select harder on the dilepton mass and on the missing transverse momentum. And we also apply a CVTO, and we use this Drell-Yan MVA to basically further suppress the Drell-Yan. So now I show you several distributions. It is important to mention here that we have 4 categories as signal regions, the 2 flavor categories, the different flavor and same flavor pair. And also we consider 2 jet multiplicity categories, events with 0 reconstructed jets and events with 1 reconstructed jets. So these distributions correspond to the different flavor channel in the 0 jet bin, where the WW prediction is shown in blue. And from left to right, we have the leading lepton PT, the trailing lepton PT, the PT of the dilepton system, the delta phi between the 2 leptons, then we have the missing transverse momentum and the dilepton mass, finally. And well, you can see that we get a quite good data Monte Carlo agreement. And same for the one jet category. Here we have the TT bar contribution in yellow. Okay. And that's all from the sequential analysis. So moving now to the random forest analysis. So it is based on a random forest multivariate technique that provides very good performance while avoiding overfitting. So we basically apply a basic dielectronic preselection that I put there. And after that, after applying this preselection, the largest contamination comes from Drell-Yan and TT bar. So we train basically two independent random forests, one versus Drell-Yan and one versus TT bar. And the hyperparameters are optimized through a grid search. So on the right side, you can find the features that have been included in the training that well, corresponds basically to the typical variables that describes the dilepton plus miscibility signature. And on the bottom, you have the optimized architecture that we have found. And well, on this slide, I show you the event selection that the random forest approach applies. So at the end, it is quite similar to the sequential analysis one, but here we add a selection on each trained random forest scores, where the cut values on these scores are optimized by minimizing the uncertainty in the cross-section and also maximizing the signal purity. So here I show you the distributions of the two random forest scores on the upper plots, and on the bottom we have the Drell-Yan random forest when selecting on the TT bar score, and on the right side the TT bar random forest when selecting on the Drell-Yan score. So keeping all this information in mind, the first result we get is a total cross-section measurement, for which we feed basically the predicted yields to the data events by included information from several control regions in the global feed. So for the sequential analysis, we include, as I said, 4 signal regions, the ones from the flavor categories and the ones from the NGETs categories. And we include also 4 control regions by just inverting the VB2. While for the random forest, in the feed, we have one single signal region, one top control region, a Drell-Yan control region, and a same sign control region. So below, you can find the sequential analysis results for each category individually and also for the combination, and then the random forest results. You can see that the results agree well with the theoretical prediction within the uncertainties. And one final thing to remark here is that although the random forest gets a purer signal region, that is true, the problem is that its sensitivity is concentrated at low WWPT due to the jet multiplicity variables that are used in the training. So at the end, this approach is more sensitive to theoretical uncertainties coming from the PTWW spectrum correction, that correction that we basically apply. And this is shown on the right plot. So there you can see the signal efficiencies of the random forest selection in blue as function of this PTWW that is basically concentrated at low values, while the efficiency for the sequential analysis selection is plotted in red. And here you can see that it is much flatter over the PTWW range. So that's the main reason why the sequential analysis gets a slightly smaller uncertainty on the cross-section measurement. So then we also measure the fiducial cross-section, and for this we define a fiducial definition at the generator level, consisting of 2 dressed leptons with PT greater than 20 GeV, eta less than 2.5. Then we select on dilepton mass greater than 20 GeV, dilepton PT greater than 30 GeV, and then the missing transverse energy greater than 20 GeV. And again, we just let the fiducial signal events flow to the data within the feed. And the results we get, as you can see, are in agreement again with theoretical prediction. And well, one final thing that the theorists requested us was to measure the fiducial cross-section in the zero jet beam by varying the jet PT threshold that defines this zero jet beam. And this is what is shown on the table below and on the plot on the right. And again, the results agree pretty well with the predictions within the uncertainties. So we also measure the differential cross-sections in beams of the lepton mass, leading lepton PT, trailing lepton PT, and delta phi between the two leptons. So for doing these measurements, we use the same fiducial definition, and we define basically several signal strengths at generator level and that are fitted in RICO beams. So there in this simultaneous fit, all the correlations between the beams are taken into account. And on the right plots, you can see the results we get that are again in good agreement with the predictions. So lastly, we set limits on the Wilson coefficients that could affect the WW production through anomalous couplings, where the effective field theory settings or effects are simulated in MathGraph. So we basically use the different flavor final state from the sequential analysis, and as observable, we choose the dilepton mass distribution that is showed at the bottom plots for the two jets categories. Okay. And well, these are the limits we get for the three coefficients through the likelihood scan that are, well, basically between a factor 2 and a factor 3 stronger than the ones that CMS got in the rank 1 analysis. That is the red squares there. And well, in this nice summary plot, it includes basically both Atlas and CMS constraints on the three coefficients, where I have marked there with the red asterisk the results coming from this particular analysis. And overall, you can see that we get up to now, well, we provide more or less the strongest limits on the three coefficients. So, okay, so that brings me to the summary. So the WW production and 13 GB results using CMS full 2016 dataset experiment have been shown, including essentially the total WW cross-section measurements, the fiducial and differential cross-section measurements, and the limits on the Wilson coefficients. And our plan for the future is to include a whole CMS rank 2 luminosity for a differential plus anomalous couplings analysis, and to make it public by the end of this year. This is our current plan for this analysis. And well, that's all from my side. So thank you. Hello.
Hello, can I ask a question, please?
Yes, sure.
So I was wondering about the random forests. It looks like the result is really different, although they are, the sigmas are kind of touching each other between the random forest and SEC, but they still are very different. So my question is first, if I understand correctly, random forest is only used to estimate the inclusive measurement.
Mm-hmm.
And then, so how would you trust this random forest result? And is there any other process you can test it?
The point is that it is mostly based, well, it is biased, let's say, to the zero jet beam. And in the zero jet beam, here you can see that it basically is selecting this low PTWW part that correspond to the basically to the zero jet beam. And well, it is true that there is tension here, but if you compare this final result from the random forest here with the sequential analysis results coming only for the zero jet category, you see that, well, we have also this excess. I mean, taking this, although of course the two event selections coming from the two analyses are quite different. Okay, but only based on the zero jet beam, I think we can make a fair comparison between the two.
But also random, I mean, okay, random forest tends to take the zero bin, but generally it also considers the, well, I mean, one jet events and so on, right?
What?
Or,
Sorry, I missed.
So it's not that, I mean, you're saying that if we compare the zero jet events, then they are very similar. But then sequential kind of takes also into account the other events which have one jet and more. And random forest kind of doesn't. Maybe I didn't get it right.
Yeah, well, in the sequential, we basically split the events and we take only the ones from the zero jet category and the ones from the one jet category. In principle, the random forest is an inclusive measurement, but given that they use jet-related variables in the training and the WW signal is mostly concentrated in the zero jet beam, then they although they want to make an inclusive selection, at the end they are mostly selecting events coming only from the zero jet beam.
I see. So this is because the other process has a signature in the number of jets. That makes it okay. Thank you very much. Yeah.
And my apologies for that. My computer froze earlier and I was muted and I was screaming while none of you were hearing me. Sorry. Are there any other questions for Pedro? All right. If not, thank you again. And we can move to the next talk, which is by Christophe Royon.
Yes, so let me share the screen.
Yes, go ahead, share your screen.
So can you see my screen?
Yes, we can share your screen. So yeah, so our next talk is Christophe Royon from the University of Kansas, and he's going to tell us about anomalous coupling studies with forward protons at the LHC. Take it away.
Okay, so thank you. So I will start by briefly introducing what is proton tagging at the LHC, because we are probing basically anomalous coupling using intact proton in the final state. Then I will discuss basically the 4 kinds of anomalous coupling, so gamma-gamma to gamma-gamma, so diphoton, gamma-Z, also WW production, and briefly ZZ production. And also I will mention the possible search for axion-like particles. So let me start by introducing you what we call PPS or CT-PPS for the CMS totem precision proton spectrometer. And there is a small sketch on the top of this slide which shows the CMS. And in fact, it's only one side of CMS which is represented here, but you should imagine that it's true for both sides of CMS. So basic man-pod detectors in order to detect possible intact protons in the final state. So if you want to get more details about this project, so I put the reference here, which is in CDS at CERN. And the idea is to use the LHC magnets, which bend the scattered proton, because the scattered protons lose part of their energy. So they are scattered from the beam, basically. And that's why by moving the proton detector close to the beam, we are able to detect and measure this intact proton in the final state. So I should say that there has been about 115 inverse femtoband of data which have been collected, for instance, in CMS and Totem, and they are being analyzed, and the results should come out very soon. And there are similar detectors in Atlas, which is called Atlas Forward Proton or IFP. So in order to have some feeling on what kind of mass we are sensitive to, I just put here 2 kinds of diagrams. The left one is a QCD diagram. I mean, in order to explain that the protons are intact in the final state, you need to have a colorless exchange. So this diagram is the so-called Causet-Martin-Riskin diagram. So where you have basically 2 protons intact in the final state, and for instance, 2 jets. And the right diagram, which will be the one that will be more interesting for us, is when you have photon exchange that can produce also a system X, and this system X can be 2 photons, a pair of W, can be a gamma Z, as we will see in the following. And I just want to show you the bottom plot, because the bottom plot shows you what is the acceptance in percent of this PPS detector as a function of mass. So what I'm meaning as a function of mass is either the mass of the 2 jets or the mass of the system X in the case of gamma-gamma interaction. So what you see immediately that the acceptance, depends on how close you can go to the beam, okay? But basically, it goes between 500 GeV up to beyond 2 TeV. So it means that since we are sensitive to very high mass, that's why we can be sensitive to beyond standard model physics, because in fact, we access in this very clean environment, because for instance, we'll get 2 protons plus the system that decayed in the central part of the detector plus nothing else. So let me first discuss, the main topic, and we'll see why I'm mentioning gamma-gamma interaction in a minute. But I just want to show you 2 diagrams which are here, for instance, gamma-gamma to WW and gamma-gamma to gamma-gamma. So this proves basically the anomalous coupling of WW production or 2-photon production. Let's discuss very briefly the standard model cross-section to start with. The cross-section to produce a W pair is of the order, let's say, of 100 femtobarn, around 96. And if we ask the mass of the pair of the W to be greater than 1 TeV, we are getting a cross-section from the standard model of the order of 6 femtobarn. So it means basically with 300 inverse femtobarn of data, we will get plenty of this kind of events, which means that this is a way to study if we have some anomalous coupling that produce, for instance, this pair of W. There will be some sensitivity to beyond standard model physics. So gamma-gamma interaction. And this is illustrated on this slide where I discuss, again, the 2 components. So for instance, I want to get 2 photons in the final state, and of course, my 2 protons intact as well. So as I said, so the left diagram is the QCD1, where you can have some gluons which are emitted. And again, you need at least 2 gluons in order to get a colorless object. And you can produce 2 photons by a loop, which is here in the middle. On the right diagram, this is a QED diagram, so photon-induced process, where you have the photons that couple again to a loop. You can get a loop of quark, a loop of leptons, or a loop of W bosons, and you can get these 2 photons in the final state. The bottom plot shows you the cross-section for this kind of events, so for a mass which is above the value in abscissa. So you have here 20 GeV, and here is about 200 GeV. So you notice immediately that the purple curve that corresponds to the left diagram, so the QCD contributions, is decreasing very fast as a function of mass. I remind you that our acceptance for the forward proton detectors, they start something like at 400 or 500, which is basically outside this plot. Whereas the contribution from the QED diagram is the dashed line, which is here in black. So you see that basically above a mass of 100 GeV or 150 GeV, you can forget about the QCD contribution with respect to the QED one. That's why there is an important conclusion. If we measure 2 photons and 2 tagged protons, this means that we have a photon-induced process. So in the following, we can neglect the contributions from the gluon-induced process. This means that basically we are concentrating of a photon-photon collider. We see the LHC as a gamma-gamma collider. Okay, so now let's motivate a bit why we want to study, as an example, quartic gamma-gamma anomalous coupling. So there can be 2 kinds of diagrams which are shown here. Either the gamma-gamma to gamma-gamma coupling can be modified by loops of new particles or via a new resonance, which I call here X. So in that case, we can introduce 2 effective operators at low energy, which are written here on the slide. And the first way to modify the coupling, as I said, is the left diagram. In that case, the coupling, for instance, zeta1, which is here in the Lagrangian, is proportional to the force power of the charge of the particle in the loops, divided by the force power of the mass, and also proportional to the spin of that particle. So this means basically for typical beyond standard model events, we can expect zeta1 of the order of 10 to minus 14, 10 to minus 13. So the other possible diagram, as we said, is the right diagram, which is a resonance. In that case, my term, this new coupling zeta1, is proportional to Fs, which is the gamma-gamma to X coupling, to produce the resonance, divided by the square value of the mass of that resonance, and again, proportional to the spin. Again, if we assume that we are looking, for instance, for 2 TeV dilatons, this will lead to a coupling of the order of 10 to minus 13. So what we need to do now is to know, are we sensitive using this kind of new method to this kind of couplings at the LHC or not? So of course, you can guess that it will be the case. If not, I will not mention it in this talk. But just do one small aside, and probably it's not really needed by this audience, but I want to remind you what is pileup at the LHC. So we have in the upper kind of drawing where we have these 2 photons, and the 2 protons are coming from the same interactions. And what we will see that the nasty background at high luminosity is, of course, as you know, we have plenty of interaction at the LHC at the same bunch crossing. So there can be basically one interaction producing my 2 PT photons, 2 high PT photons, and some additional interactions or pileup that produce my intact proton in the final state. So we need to be able to distinguishing these 2 kind of processes, because again, we get up to 50 pileup events per bunch crossing at the LHC. So how are we going to do this? So let me first of all mention the order of magnitude for the cross section. So I will just remind you, this is the process that you are considering. This is gamma interaction, which is going to 2 photons. And on the bottom plot, this is the number of events as a function of the mass of the diphoton mass, which is here in the final state. In black, you have the values for 2 anomalous coupling, 10 to minus 12 or 10 to minus 13 GeV minus 4. So this is for 300 inverse femtobarn and a pileup of 50. And basically, you see that all the background events are represented here in purple, for instance, in green, which correspond to exclusive background from the standard model or double Pomeroy exchange background. But basically, what you need to remember is that this background is extremely small, so you can forget about it. The only one which matters is the red curve. You see that it's basically the same order of magnitude as our signal. And this corresponds to what we just introduced, so 2 photons plus the proton coming from pileup events. So this is what we need to fight if we want to get a clean sample of potential beyond standard model events. So how are we going to do this? And this is where the fact that we detect the proton is really crucial. Since we detect all the particles in the final state, basically we are like at LEP. I mean, we have a very clean events. We measure the 2 protons, we measure the 2 photons, and there is nothing more in that kind of events. Which means that we can measure the kinematical properties either by measuring the 2 protons in our Raman pot detectors, or by measuring our 2 photons, for instance, in CMS or Atlas. This is, and for our signal, these kinematical properties should be the same. So it means that for the signal events, for instance, the mass of the 2 photons should be the same as the mass of my 2 proton system. And this is the same for the rapidity distribution. So this is illustrated on the next plots, the upper plots that you can see, where you see here the ratio of the mass of the 2 protons divided by the mass of the 2 photons for the signal. So this is the black peaks, which are here. And for the pileup events, which is in red, which is almost a flat distribution, because of course, as we know for pileup events, my 2 protons have nothing to do with my 2 photons. They originate from different interactions. And this is the same for the difference in rapidity between the 2 photon and the 2 proton system. So you see immediately that if we cut on these 2 distributions, the background will become negligible. And this is, I don't want to enter in the detail of all the numbers because of lack of time, but I just want to mention that after this exclusivity curve for 300 inverse femtobarn, you get a background which is negligible, which is expected to be 0.1 events. Whereas, for instance, for some values of anomalous coupling, you can expect 170 events. So basically, what I want you to remember is that using this kind of techniques and measuring the proton in the final state, we have no background for 300 inverse femtobarn, which leads to a sensitivity up to a few 10 to minus 15 GeV minus 4 on our coupling, which is better by 2 orders of magnitude than the standard methods that are used at the LHC. So this will reach also basically the values that are expected for this kind of anomalous coupling events. That's why it's interesting to look for this event using this method. So let me now mention another application. So as we said, I mean, we can produce this kind of events if there is a new resonance that decay into photons. And what we discuss here is the sensitivity to axion-like particle, again, produced as a resonance. We use exactly the same method. We measure the two photons in the final state plus the two intact protons. And what is shown in the axion particle, these are the present sensitivity that we have coming from LHC, or Tevatron, BLEP, and so on. And what you see is the additional possible sensitivity in gray that we can use using this kind of additional method. So, and this gives much better result than the usual method at the LHC, which is usually that people look for the Z boson decay into 3 photons, and we gain again in sensitivity by about 2 orders of magnitude. So let me just mention briefly that there is also some complementarity with respect to the heavy ion runs, because you might know that the photon coupling in heavy ions is enhanced by a factor which is Z to the 4. So basically, when you are using lead, you increase a lot the cross section. But the problem is that since the heavy ions are quite big, you cannot produce high mass objects. So just to show you on this plot, which is here on the left, you see the sensitivity that we just described in gray, in grayish color, which is in proton-proton interaction. And this is the sensitivity in the dashed line that we will have for proton-lead, lead-lead, or argon-argon interaction at the LHC. And again, you see that we are sensitive in the low mass action region, which is more of the order of 10 GeV up to 100 GeV. Whereas when you use proton-proton interaction, we are more sensitive. We have some sensitivity in the TeV range as expected. Okay, so let's move to another anomalous coupling. It will be exactly the same, except now, instead of having 2 photons in the final state, I assume that we have 1 photon plus 1 Z boson. Exactly the same plot as before, where you see here the number of events for 300 inverse femtobarn as a function of the mass, the gamma Z. The signal is in black, and our background, as you can guess, in red, that corresponds to gamma Z plus pile-up protons. So this is the one we need to find. We use exactly the same technique, meaning that we compare the information from the 2 protons from the information from the gamma and Z boson. What we do, that's why I wanted to mention this new aspect, is that we look for Z boson that decays both leptonically and also for hadronically, which enhance, of course, the cross-section of the events that we can measure. So that's why here in the mass comparison, you have a much broader peak than we had before. I can show very briefly what we had 5 seconds ago. Here is the plot. You saw that the width of this, the mass from the 2 photons was very small because there is a very good resolution on the diphoton mass. But now we get much worse resolution for the events when the Z boson that decay into 2 jets. And this is especially where this plot comes from. Again, by using the same technique, comparing the mass of the 2 protons and the mass of gamma Z in the final state, and also the rapidity of the 2 protons and the rapidity of the gamma Z system, with 3 in red inverse femtobarn, we gain, in fact, about 3 orders of magnitude with respect to the usual sensitivity at the LHC. So again, and also the advantage of this method is that we are sensitive to anomalous coupling in a model which is completely independent way. We don't depend on any models, because if we measure, for instance, some anomalous events or anomalous production of gamma Z events, this could be to any reason that produces some anomalous coupling. I mentioned, for instance, axion particle. It could be composite Higgs, or it could be also extra dimension. If we see something, we have to go back to these events, for instance, angular distribution, to understand what is going on. Okay, so let me move to the last part of the talk. What I wanted to mention is to discuss also briefly the standard model observation and anomalous coupling in WW events. Exactly the same kind of production, photon-induced processes, and I'm having 2 Ws, W plus and W minus, in the final state, with the 2 protons intact as usual. So what we are looking for now is the different decay of the W pair. There is obviously the purely leptonic decay, so lepton plus neutrino, lepton meaning electron or muons. There are the semi-leptonic decay, where you have one decaying in leptonically and the other one in fat jets, or the W plus, W minus decaying in two fat jets. What we studied, concerning the standard model prediction of exclusive WW, we considered only the leptonic decays for these studies. For 300 inverse femtobarn and the after selection, we have about 50 events that can be produced from the standard model for 300 inverse femtobarn and 2 background events that are predicted. So clearly, for the next run at the LHC, this would lead to a possible expectation to observe these WW events with proton tagged in the final state at very high mass, which has never been observed so far at high mass WW pair. Now, let me comment briefly the bottom right diagram, where you see the standard model is in red, and the anomalous coupling events is here in black. So for a value, for instance, which is here 5, as an example, 10 to minus 6 for the coupling, or 5, 10 to minus 7. So what you notice immediately is that the anomalous coupling events are produced at higher mass. And this is why this will change our strategy to detect this kind of events, where basically we had to use the leptonic decays for the standard model because they are at low mass. And of course, the dijet cross-section is huge at low mass. So this would be a direct background when we look for WW decaying into fat jets. Since we are at high mass for beyond standard model events, we will be focusing on the WW decay into two fat jets. So let me show you the results. So this is basically, for instance, for an anomalous coupling of 10 to minus 6, GeV minus 2. We expect about 110 events for 300 inverse femtobarn for a background which is 87 due to pilot event, as usual, in using basically the WW decaying into two high PT fat jets. So this leads basically to a sensitivity which is of the order of 4, 10 to minus 7, GeV minus 2. I just remind you that the present limits are of the order of 10 to minus 4. So we gain, again, more than 2 orders of magnitude using this method to look for the exclusive production of WW, and who knows, maybe some anomalous production. So I just want to conclude now. So basically what I introduced you is the way to get the LHC as a gamma-gamma collider. We studied a few different anomalous coupling. What we showed is that these kind of events are photon-induced processes, because we showed that the QCD contribution is close to 0. So we are completely dominated by photon-induced processes. Of course, compared to QCD, the theoretical calculation is in better control because we have QED processes. This is, between quote, a background-free experiment. So any observed event will be signaled. Also, we probe, for instance, BSM diphoton production or gamma Z production in a model-independent way. This can be due to different models. And then we'd have, of course, if we see some excess, we'll have to interpret this result and see what is happening. And also, I mentioned basically at the end that there is also a possibility to observe this exclusive WW production using about 300 inverse femtobarn of data at the LHC. I just want to finish by showing a small cartoon. So basically, this is a new method that to look at the kind of anomalous coupling with intact photon in the final state. And this was the reason to basically to have the Roman pot taking data all the time. So anytime that CMS or Atlas is taking data, we are recording the intact proton in the final state. So I would just say that not like these people, but we need to look everywhere, because who knows where we can find beyond standard model signals. So thank you very much.
All right, thank you, Christophe, for that talk. Are there any questions from anyone? I had one question regarding, you talked about this quite a bit, but I think I didn't follow one point on the pilot mitigation. So you were trying to deal with the protons coming from the pileup by looking at the, I guess, the invariant mass of the protons to the 2-photon ratio, and then you were cutting out some of the pileup background. But isn't there like a combinatorics problem there, like in the, not this plot, but the next slide? Let's see.
This one, yeah.
No, yeah, this one right here. So here you're computing this ratio of the, I guess, the diproton mass to the diphoton mass.
Yeah.
And then you're picking out you're cutting out the smooth pileup background. But don't you encounter a combinatorics problem here, in the sense of which 2 protons do you use to construct the mass? I didn't quite follow that.
Sorry, I didn't enter into the detail, but what we choose, for instance, for this plot, and of course it's a bit arbitrary, we took the 2 protons that lead to the highest mass, because we know that we want to look at very high mass events. So we choose, for instance, if we have 4 protons, we took the combination. Of course, we ask 1 proton on, or at least 1 proton on each side, I mean, for sure, of CMS. So they need to be on both sides. But when there are more than 1 proton on each side, we just take the combination that lead to the highest mass.
I see. Okay, thank you. Aram?
So there could be other choice. I mean, for instance, since we know the mass of the 2 photon in CMS, we could choose the ones that lead to the closest mass of the 2 photon mass. This would be another possibility, but it's not what was done for this plot.
I see. Okay, thank you. Aram?
Thank you.
Yeah, Christophe, I just had one quick question. It was very interesting to see this axion sensitivity to axion searches in these heavy ion collisions that you mentioned. One thing I was wondering, this 10 inverse nanobarn exactly in this plot that you are showing. So do you know if Atlas and CMS already have some data with forward proton, or this is in the plot here says what is possible?
Yeah, so sorry for the confusion about it, because I was fast. But in fact, for this, the big advantage of this heavy ion collision is that we don't have pileup for this heavy ion collision, contrary to proton-proton collision, because there is not such a high luminosity, of course. So basically, what we use, the technique for this heavy ion runs, is just asking nothing in the forward direction for the forward detectors, that's it. So we measure 2 photons, for instance, in the central detector, and we ask no activities in the forward part of the detector.
Okay.
So we don't need to tag the lead or this intact heavy ions, because in fact, the acceptance, for instance, in proton lead events, the acceptance for the intact proton would be completely different, because the beam lattice is very different. So we have 0 acceptance to detect these intact protons in the Raman plot.
Okay, makes sense. Thank you.
All right. Thank you again, Christophe. We'll move on to the.
Stop sharing.
Yes. Our next talk is by Max Goblirsch-Kolb from Brandeis, and he'll be speaking on behalf of the Atlas collaboration on recent observation and measurements of vector boson fusion and scattering with Atlas. Take it away, Max.
Thanks a lot. Just to confirm, you can see my slides, you can hear me?
Yes, we can hear
Wonderful.
you and see your slides. Yep.
Thanks a lot. So thanks for the invitation. And indeed, I'm going to talk to you a little bit about the vector boson fusion and scattering in Atlas. So maybe first of all, just to motivate why we want to talk about this, why we want to measure this. One of the main goals of the LHC is to study the nature of electroweak symmetry breaking. Now, one way we can do this is, of course, to measure the interaction of the gauge fields with the Higgs field. We've had some talks on this already. But in addition, we can also directly look at the self-interaction of the gauge bosons at high energy scale. And this is where vector boson fusion and scattering really comes in. So naively, the classical search channel that we think of, initially at least at the LHC, is something like what I have here on the slide at the top right. You have your incoming partons, they radiate gauge bosons. Those interact with each other, may be governed by the standard model, may be governed by BSM effects. This is, of course, interesting to find out. You get your bosonic final state, and then you have this characteristic recoil topology where you have the 2 outgoing scattered partons, which tend to go in the forward directions with fairly high momenta without jet activity in the rapidity gap between them. So this is naively when you tell someone at the LHC about vector boson fusion or scattering, what they think about. There are, of course, also interesting special cases. We just heard about one, photon scattering, in which case you can leave your initial proton intact, which gives you a whole range of interesting experimental topologies, which I'll also briefly mention later on. So this is obviously something challenging to measure at the LHC. Just from the number of electroweak vertices, we know the cross-sections are not going to be very high. This is a rare process. And it doesn't occur on its own either. So we have always at the LHC to contend with multi-jet background activity. This means we are usually constrained to leptonic or at least semi-leptonic final states with an according penalty and branching ratio. And we have competition from strong diboson or single boson production in association with jets. Now, these jets can either come from your hard scatter interaction, like in the example I show here on this slide, but they can also come from pileup, and this can be non-trivial to distinguish from the jet activity from the hard scatter, in particular because these jets go in the forward direction. In addition, we should also not forget that there are also other electroweak production modes for the same final state, for example, shown here at the bottom right, that are not occurring via vector boson fusion or scattering. So again, something to keep in mind. What we typically try to do to escape large modeling uncertainties is to use collision data where possible to reduce these uncertainties and to constrain backgrounds. The issue is, of course, given we have both low rates to start with and we have to constrain backgrounds, we will need a large data set for these measurements. And this is why LHC Run 2 is so interesting for this. It has essentially allowed us a first full run of these. So in this talk, I'm going to try to walk you through a few highlights of these measurements and also give you a short glimpse at some non-standard topologies. Let's start by looking at Z-boson plus dijet production in Atlas. So this is a process which can occur via a vector boson fusion diagram, indeed. We also have the non-vector boson fusion electroweak component I alluded to, and we have strong production. So this is a classical example. What we are after here is to measure both the inclusive process and the electroweak one. Why? Because both are actually very challenging to model, and any improvement here will be beneficial not just for understanding this process, but also for modeling of other backgrounds in these kinds of measurements. We perform this measurement in an electroweak enriched phase space. We start out by selecting the leptonic decay mode of the Z boson, which luckily already removes most of the non-Z boson backgrounds. And then we require this typical VBF topology I mentioned. So we select two high energy jets in the forward direction with a large rapidity gap and a high dijet invariant mass. And then we require basically that our Z boson system is central compared to this dijet system. We also reject additional jets from pileup by requiring a momentum balance in a transverse plane between the dijet system and the Z boson. The resulting data sample is shown on the bottom right of the slide, in this case for the dijet mass distribution. You see the dominant contribution here in blue is the strong ZJJ production, and in red at high masses you also accumulate the electroweak component. The other backgrounds, as you see, are very small. Those mainly consist of diboson processes with one hadronic boson decay as well as TT bar. Now, how do we extract cross-sections from this? First of all, we of course want to know what we actually measure. In this case, we're interested in three observables which characterize our dijet system. This is the dijet invariant mass, the rapidity gap, and the signed dijet azimuthal angle, which is very interesting because it's sensitive to CP violating effects. In addition, we are also interested in the recoil transverse momentum of the Z system. When we just want to measure the inclusive process, this is fairly simple because the remaining process backgrounds are very small and can simply be subtracted. It gets more difficult when we want to measure the electroweak component because we saw that there is a very significant strong production at mixture, and this is not extremely well modeled. So we want to constrain this using data. To do this, we add three additional regions in addition to our signal region. These are defined by either allowing additional gap jets in the rapidity gap between our two tagging jets, or by loosening our requirement on the Z boson centrality. And then what we can do is basically reinforce the correlation across this region for the strong component and perform a combined fit where the excess yield in the signal region is then attributed to electroweak. You can see how this works in the bottom left, where we start out with the raw prediction compared to the data observation. And then you can see how the fit assigns this to the two processes in a way where the sum of the processes basically matches what we see in the data. And then in both cases, what is left to do is to translate these yields into cross-sections by correcting for detector effects in an unfolding procedure. Let's look at some results. So let's start by talking about uncertainties very quickly. On the top, you see a measurement of the dijet invariant mass spectrum in the inclusive case. What you see here in blue for the uncertainties is that one dominant component are jet energy scale and resolution uncertainties. And then we add to that at high masses also statistical uncertainties. The resulting measurement is shown on the top right. You can see the data in black with gray error bars, and you see that these error bars are actually smaller already than the theory uncertainties on the predictions, which are shown in green and blue. So this means we are already at a level where we can actually start to constrain theory predictions and see which kind of generator tunes, for example, are preferred, which is very interesting and useful. For the electroweak measurement, you see an uncertainty plot for the Z-boson BT measurement at the bottom. You see we gain this large blue contribution, and this is from subtraction of the strong ZJJ. In spite of the data-driven approach, this does bias a large uncertainty. The resulting measurement is on the right, slightly larger errors, obviously, but you see we are still able to distinguish between different Monte Carlo predictions and already see which ones maybe do a slightly better job of describing our data at this point. So this is very nice to see, and it's exactly this input to future modeling that we are after. In addition, we can now use these measurements to extract some limits on BSM models, which I'll unfortunately not be able to show in the main part of this talk, at least due to time constraints. So now let's look at vector boson scattering in a diboson final state. In this case, we will look at the rarest one there is, Z-boson pair production in association with two jets. Now, the electroweak process, of which I show a few examples here on this slide, has a competing channel which is much more frequent to start out with, which is strong production of these topologies. And this is the main challenge. We have to subtract this. In ATLAS, to try to establish initial observation, we combine the fully leptonic and the semi-leptonic decay modes of the ZZ system. To obtain acceptable yields while having a fairly high sensitivity, we combine a standard diboson selection, which either selects a 4-lepton or a 2-lepton plus missing transverse energy system. And then we add the requirements on the tagging jets, which I already explained in the previous measurement. So this is almost the same principle here. The resulting region is fairly pure already in ZZ events. You can see this on the bottom right-hand side. The left column is 4 leptons, the right column is semi-leptonic. For the 4 leptons, you can see we basically only have ZZ with a fairly large contribution of QCD, which we will have to deal with later. In the semi-leptonic case, you see in addition to ZZ, we also have some additional backgrounds. This is WW, TT bar, as well as WZ, where you miss 1 lepton. And these are estimated using simulation and then normalized in dedicated control regions and subtracted. Now what we have to do is to discriminate between the strong and the electroweak component. And to do this, we use multivariate discriminants, which use the lepton and jet kinematics in the event and basically enrich the electroweak signal at high values. You can see this for the 4-lepton signal region on the top left-hand side and for the semi-leptonic case on the right. The uncertainties in these distributions are currently still driven by statistics with some additional uncertainty impacts from lepton efficiency modeling and theoretical modeling of the various processes. To then extract the signal, we perform a combined fit of these two regions, as well as a third region, which I'm showing on the bottom right, which is a signal depleted control region intended to normalize the QCD ZZ in the 4-lepton case. Combining them, we get signal strength parameters for our various processes, which are shown in the table here. You can see they are both individually and in their combination consistent with the standard model. And we are able to exclude the case of no electroweak process at more than 5 sigma significance, meaning this is the first time we can observe this process in ATLAS. We can also extract fiducial cross-sections by correcting for detector effects. And we find cross-sections values which are again in agreement with the theoretical prediction at this point. Now, let's look at something non-standard, which we actually already heard a bit about in the previous talk. So if we have photon scattering and in this case, W pair production, this can give us the very interesting scenario where we actually leave the protons intact. This gives us a unique topology in the detector because all we expect to see, at least for this interaction, is the decay products of the W. Now, in this case, we're looking at the leptonic W decay. So what we see in the detector is something like what we show here on the bottom right in an event display of a candidate. You basically have a vertex with 2 leptons emerging and no other charged particle activities nearby. So this is very striking and unique and something we can look for. In this case, we do a track counting based analysis. So we count tracks in a certain window around the lepton pair vertex. We do not apply proton tagging here. However, we heard already that this is also a very interesting avenue in this direction. So obviously, if we want to do a track counting analysis, we really rely on accurate modeling of the track density around the dilepton vertex. This requires very careful calibration of the track multiplicity, both in the pileup, which affects our signal efficiency because you can have pileup tracks overlap with your signal vertex, and for the underlying event, because events from other processes where you have no tracks in acceptance do, of course, form a background source. So in both cases, we have careful corrections applied to the simulation to make sure that we describe the data correctly. On the top right-hand side, you can see one example where we use a random sampling technique, look at the track density around a random location along the beamline, and then essentially compare to our data, which is shown in dots, various corrections applied to the simulation, where the fully corrected Monte Carlo really closes very nicely. In addition, we also apply data-driven corrections to our signal in order to account for rescattering effects, so interactions between the two protons after they produce the W pair, as well as single and double diffractive events, which are not included in our simulation out of the box. And to do this, we use exclusive dilepton events, also photon-initiated, where we use the measured rate and compare this to elastic simulation, essentially, and then obtain a transfer factor. In all this, the main uncertainties come from track reconstruction efficiencies, which affect in particular the background, where we miss tracks and thus gain events, non-point lepton modeling, where we have a data-driven estimate in place, as well as theoretical modeling of signal and background. To extract the signal, we look at different flavor events to get rid of exclusive dileptons, veto any tracks, and require a certain recoil momentum of the lepton system against the neutrino switch escape. We use the sidebands of this selection to constrain the background further. At the bottom left, you can see one such sideband in a region where we actually have some tracks in the event. You see this is completely background dominated and allows to nicely constrain the normalization of both Drell-Yan and WW. And then the signal region without jets is essentially appearing when you veto any tracks. You see at low momenta, you have Drell-Yan, but then at high momenta, you really have a nice signal at mixture. You can also see in the track multiplicity plot how the signal really accumulates at 0 tracks in this case. The measurement rejects the background only hypothesis at over 8 sigma, so this is a clear observation, and we measure a signal strength which is compatible with the corrected standard model prediction. The same holds also for the fiducial cross-section, which we can then extract from this. Now to close out, I want to show you something maybe even a bit more exotic actually, which is lead-lead initiated photon-photon scattering. So here we exploit the absence of pileup and a strong electromagnetic field in these heavy ion collisions to probe light-by-light scattering. Obviously, since we have a very small data set, we do this in a very soft region of the phase space. So what we look for in this case is something very unlike what you would normally expect from heavy ions. 2 soft photons, no other activity in the detector. In particular, no charge tracks. This is already challenging to trigger. So we operate a dedicated trigger chain just for this measurement, which requires a certain low amount of calorimetric deposit and vetoes, in particular the forward detectors, which would otherwise be a sign of fragmentation. The phase space of the measurement is then really just, we fire this trigger and we have as the only activity in our event 2 soft photons, nothing else. And this diphoton system should be close to rest. The only backgrounds here are exclusive electron pair production, where we miss the tracks belonging to the electrons, which we can estimate using data, and central exclusive production, so a gluon-initiated process, which we can estimate in simulation, which is normalized to data in a region where we loosen the echoplanarity requirement on the photons. A huge challenge in this analysis is obviously to calibrate this low momentum reconstruction and the dedicated triggers. I won't be able to cover all of this effort, but just to show you one example, on the bottom right, you can see the trigger turn-on curve, which is carefully calibrated in collision data using an auxiliary trigger. You can see different triggers here for different data taking periods, where in 2018 we improved our acceptance a bit. The uncertainties in this measurement are currently dominated by statistics, but we also have contributions from background and object calibration. You can see an example of the resulting yields on the right-hand side, where the signal is shown in white superimposed on the background. We can extract a fiducial cross-section here, which is in agreement with the predictions. And we can also start to measure differential cross-sections, as shown in the bottom left here, which are currently in agreement, although with large errors with the standard model. What we can also do here is actually to place some limits on axion-like particle production models, where we essentially have an additional mediator that gives us this scattering process. And in this case, we can add a bit to the bounds, in particular in the region between 6 and 100 GeV of axion mass. So with that, let me summarize. I hope I was able to show that with the full run-through data set, we've actually already unlocked quite a bit of potential for vector boson self-interaction measurements. We can, doing this, both probe the electroweak standard model and to start looking for signs of BSM effects. These are typically rare processes. This is why this has now become so interesting with the full luminosity available. I showed you quite a range of measurements, starting from classical measurements, which exploit this typical VBF-VBS digit topology, but also more exotic analysis, which really make maximum use of all the features of our detector to go beyond the standard candle essentially and look for interesting topologies. This is challenging, but provides invaluable results. Most measurements currently are still statistically limited, so there is a lot of potential for the future in LHC 1, 3, and 4. And if you read the various yellow reports, for example, vector boson fusion and scattering measurements are also one of our main targets for the future high-Lumi LHC program. Thanks a lot.
All right, thanks a lot, Max. Are there any questions from anyone? Let me ask a question, which is, if I recall correctly, and maybe this is already part of your analysis as it is, but for vector boson fusion production, when you look at the QCD background, yes, that's previous slide you just showed, the one after this, I guess.
Yeah.
No, one more.
One more.
Where you had the Feynman diagrams with the electroweak versus the strong production.
This one maybe, or do you mean for diboson?
For the vector boson fusion one. So you had the vector boson fusion electroweak component. Yeah, this one right here.
Okay. Yep.
So if I recall correctly, the electroweak production, the top ones there, isn't it true that those the final state jets, they tend to be a lot more forward than the jets in the diagrams in the bottom row? Is that correct?
Yes, so this is one of the things that we indeed exploit in this analysis.
Okay, so that is taken into account. So there's some sort of a rapidity gap type.
Exactly.
Okay.
So the rapidity gap and the dijet invariant mass are actually very powerful discriminants, which also go into these multivariate discriminants. One slight limitation in the ZZ final state is, of course, the statistics you start out with. So you cannot be quite as strict in defining this electroweak signal region as you could, for example, be in the Z plus JJ case, simply because you run out of events if you become too strict.
I see. Okay. Any other questions from anyone? I guess I had one more, which is regarding your lead-lead collisions. So you mentioned that the pileup is very low for lead-lead, and you said obviously, is that why is that? Is the bunch structure somehow different when we're doing lead-lead collisions, or?
In particular, the bunch density is much different. So we're running far, far lower luminosities in lead-lead collisions.
I see.
I mean, just to give you an impression of the order of magnitude, you can see in an order of magnitude of months running, we collect something like inverse nanobands of integrated luminosity compared to inverse femtobands in proton-proton.
I see. Got it. Okay. All righty. Any other questions from anyone? All right, if not, thank you again for the talk. I think this concludes our session. So I want to thank all of the speakers and all of the people for attending this session, and I hope you guys enjoy the rest of the workshop. Take care, everyone.